Chapter 7, Quantum Theory, Electronic Structure of Atoms, and Periodic Trends, featuring Brianna Delgado, Cynthia Garcia, and Cristina Guerrero for Chemistry 1311 with Dr. Delgado.
So to begin, we must understand waves so we can understand quantum theory. What are waves? Waves are the vibrating disturbances by which energy is transmitted. So when we think of waves, we think of things such as ocean waves, but the waves that we will be discussing include things like a TV, microwave, or radios. Some of the characteristics of the waves we will be studying include wavelength, which is the horizontal distance between 2 points. They are measured in meters, centimeters, and nanometers. If you can see on our bottom right picture, they're both outlined in red, the wavelength and the frequency and amplitude, Amplitude is the vertical distance from midline to a peak. And last, the frequency is the number of waves that pass through a particular point. For example, the wave can pass 20 times in 1 second, so the frequency of the wave would be 20 per second. The equation we will be using for this is U equals delta Y times V, which is the speed of a wave, is equal to wavelength times frequency. Continuing on other important points of our waves, visible light consists of electromagnetic waves. These waves have both an electric field component and a magnetic field component. Some examples of electromagnetic radiation include X-rays and police radars. These waves travel at 3.00 times 10 to the power of 8 meters per second. We're going to do a practice problem. The wavelength of green light from a traffic signal is centered at 520 nanometers. What is the frequency of this radiation? So we wrote out the problem. Again, we have the equation U equals delta Y times V. We already have U, which is the speed of light in this case, 3.00 times 10 to the 8th meters per second. And our wavelength is given to us in the problem, which is 520 nanometers. Because our speed of light is in meters, we have to convert that number to meters as well. It would be 520 times 10 to the power of negative 9. Next, since we're solving for frequency, we do have to rearrange the equation. So we rearrange it to V equals U divided by delta Y. We plug in the numbers, the speed of light divided by the wavelength, and we get 5.77 times 10 to the 14th power, times 10 to the 14th per second. So after Planck's quantum theory, we have the photoelectric effect. The photoelectric effect is when electrons are ejected from the surface of certain metals that are exposed to light. The number of electrons that are ejected are proportional to the brightness of the light. This beam of light is now known as photons, which is a stream of particles. Planck's quantum theory states that atoms absorb energy in certain quantities, also known as quantum. So each photon possesses energy. The equation would be E equals H times V. In our equation, H is equal to Planck's constant, 6.63 times 10 to the power of negative 34 joules times second. This is a number that is a constant. Anytime we see H, we will be using this number, so we'll have to memorize it. Our equation earlier, V equals C divided by wavelength, can also be expressed as E is equal to H times C divided by delta Y. So we have another practice problem. If we calculate the energy in joules of a photon with a wavelength of 5.01 times 10 to the power of 4 nanometers. Cristina will be doing this problem.
Once again, we went ahead and wrote it down, the problem and the solution, and I'll be reading along with it. Calculate the energy of photons with wavelength of 5.01 times 10 to the 4th nanometer. First, we will write down the formula E equals h times c. The E is the energy, the h is the Planck's constant, and the c is the speed of light. The wavelength was given to us as 5.01 times 10 to the 5th nanometer. I will plug in the numbers, and as I'm doing the calculation, the seconds will be canceled and the meters will cancel. I need to convert nanometers to meters and then do the formula. My answer will be 3.97 times 10 to the negative 21 joules.
Alrighty, so now we're going to go ahead and move on to the periodic table of elements. Now, if we think back to the beginning of this semester, when we first learned about the periodic table of elements, we know that it is set up the way it is into different groups. So as group A on the very far right, we have the noble gases. In the middle, right here, we have the transition metals. And on the far left, we have the representative elements. And then on these two down here, as they're already labeled, we have the lanthanide series and the acetinide series. Sorry, I don't really know how to say that. As you can see, it's also color-coded down here, and it's corresponding to the different elements. So all elements in the groups would have the same number of valence electrons. Hence, they also have a resemblance in the different chemical behaviors that they have. There's just a few slight exceptions. So we're gonna look further into this with the different periodic trends. Now, there are 3 periodic trends that we're gonna focus on for this semester. And it's very, very important that we do memorize these trends. Although we don't have to memorize the numbers corresponding with each trend, we do need to just remember the basic rule for each trend because there's going to be a lot of questions of this on our test. So we're going to go ahead and move on with the first trend, which is the ionization energy. So ionization energy, what is it? It is the minimum energy that is required to remove an electron from an atom. As we already have learned, group 1 and 2 on the far left give electrons off, and groups 3 through 7 want electrons. And of course, the farthest group to the right, which is group 8, has the perfect number of electrons, and everybody wants to be like them. They're the cool kids on the periodic table. So for this reason, the ionization energy does increase from left to right. So as we can see, helium would be the element with the highest ionization energy on the top right corner. Moving on to our next trend is electron affinity. Now, electron affinity is the negative energy change that occurs when an electron is accepted by an atom in a gaseous state in order to form an anion. So as you can see, the electron affinity does have the same trend as increasing ionization energy, as it increases from left to right and from top to bottom. So the only difference between the two different trends would be, as you can see for electron affinity, the top row, group 1, is not included on the far right. So helium would be left out on electron affinity. Moving on to our next trend, the third trend is going to be atomic size. Now, atomic size is basically just half the distance between 2 adjacent atoms. Now, as you can tell, our graph here on our PowerPoint looks a bit different from the other 2 that we just looked at, as this trend is actually backwards. So atomic size would increase from right to left and from the top to the bottom, with the element with the highest atomic size being francium. So before we move on, we're just going to go back and take a look at our beginning periodic table, the blank one. Let's see. So if during the test we were given the question, find the element with the highest ionization energy when looking at elements lithium and iodine. So if we look at our periodic table, lithium is on the far left and iodine is on the far right. Therefore, our answer would be iodine is the element with the highest ionization energy, because as we have already learned, the trend for ionization energy does increase from left to right. If we were given another question that said, for example, when given the elements calcium and sulfur, which element has the highest electron affinity? And of course, we would go back to our periodic table again. And as we already know, since the electron affinity does increase from left to right, the answer there would be sulfur. And finally, another question could be between the elements boron and beryllium, which element has the highest atomic size? And in that case, the answer would actually be beryllium, because it is farthest to the left and atomic size does increase from right to left. Therefore, beryllium would have the highest atomic size. And of course, if any of these questions were asked in the vice versa, the answer would just be the opposite. So if they're looking for the atom with the lowest atomic size, lowest ionization energy, or lowest lowest electron affinity, it would just be the vice versa of the trends that we already know. So of course, when you guys are studying at home, just go ahead and look over these trends and make sure you have them known by memory. If you need to write them down 100 times, just keep on going over practice problems, whatever y'all need to do to really understand the atomic trends, because they are very vital to your grade in this class. So now we're gonna go ahead and move on to our next topic, which is going to be quantum numbers with Cristina.
Quantum numbers. The principal quantum number, n, indicates the main energy level and distance of electrons from nucleus. The value is always greater than or equal to 1. Angular momentum number, L, indicates the shape of the orbital. The value will always be 0 to n minus 1. It indicates number of orbitals, which can be found by using 2L plus 1. Magnetic quantum number, ML, indicates orientation of orbital. The value will always be negative L to L. Spin quantum number, MS, indicates direction of electrons. Spin, the value will always be positive 1/2 to negative 1/2. Question, quantum numbers. What are the values of L, ML, and MS when n equals 5? We have n equals 5, so remember that L equals n minus 1, so we will have 5 minus 1 equals 4. Now we can put L equals 4, 3, 2, 1, 0. Remember, when L equals 0, it indicates an s orbital. L equals 1, it indicates a p orbital. ML is negative L to L, so we will put negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. And MS will be the magnetic spin, which will always be positive 1/2 or negative 1/2. If it is positive, it will be clockwise, and when it is negative, it will be counterclockwise. Okay, we are moving on to electron configuration. It is the distribution of electrons and when they are found in the atoms or the ions. It can be broken down into 4 blocks. the S block, the P block, the D block, and F block. Each block contains a different number of orbitals, and each orbital can contain up to 2 electrons. The S block has 1 orbital, meaning it can carry 2 electrons. The P orbital has 3 orbitals. How many electrons can it carry? It can carry 6 electrons because each orbital can carry 2 electrons. The D block has 5 orbitals, meaning it can carry 10 electrons, and the F block has 7 orbitals, which can carry 14 electrons.
So now that we went over all of the concepts, we're going to go ahead and do some review problems just to make sure we really get the concepts. So we're going to start off with question 1, which states, which property tends to decrease as you move from top to bottom down group 14? The possible choices are A, atomic radius, B, metallic character, C, ionization energy, and D, reactivity with oxygen. So, as we look at this problem, right off the bat, we already have 2 answer choices that we can knock off because they have nothing to do with trends. And if you look at the question, it is asking for trends. So we can go ahead and knock off answer choice B and D, metallic character and reactivity with oxygen. Those have nothing to do with it. So we are left with our 2 answer choices, which are either A, atomic radius, or C, ionization energy. So if we look back, atomic radius increases from right to left and from top to bottom, and ionization does the opposite, which increases from left to right and from bottom to top. So this is one of those questions that is asking us for the vice versa. It's asking which one decreases as you move from top to bottom. So if we go and look at group 14, which by the way, it does not matter if it's group 14, 15, 16, 13, whatever the case, remember the trends are the same for the entire periodic table of elements. So our answer would be C, ionization energy, because it increases from bottom to top, meaning it decreases from top to bottom. So our answer is C, ionization energy. Moving on to question 2.
Arrange the following atoms in order of electron affinity. Chlorine, sodium, and silicone. So we shaded the elements that are in question. We have chlorine, silicone, and sodium. So if we look back at the electron affinity trends, we'll remember that it increases from left to right and bottom to top. So in increasing electron affinity, it would be sodium would be less than silicone, which is less than chlorine.
Moving on to question 3, which says, arrange the following atoms in order of increasing atomic radius. And our elements given to us are P, K, and N. So if we look at our periodic table, P would be phosphorus, K is potassium, and N would be nitrogen. So if we're going to order these in order of increasing atomic radius, we must remember that atomic radius does increase from right to left and from the bottom to the top. So our answer would be, as shown here on the paper, it would be N, P, and then K. So K would have the highest atomic radius since it is farthest to the left on our chart, and then so on and so on. It goes on with the trend. Moving on to our question 4.
Write the complete electron configuration for the following atoms: NaMg. will equal to 1s2, 2s2, 2p6, 3s1. Mg will equal 1s2, 2s2, 2p6, 3s2. There is another way to get this number. I wrote down the long version notation, but there is also a shorthand notation. It simply means that you can look at the noble gas before. For example, we are working with Na. The noble gas before is neon, so we put Ne in the brackets. Since it already has 10 electrons and we need 11, we count the electrons. 6, 8, 10, 11. And now we add neon with 3s1, and that will give us the short version hand of the total electrons. Now I'm going to show you how to write the electron configuration of chlorine. Chlorine has 17 electrons. The first orbital has 2 electrons. The second orbital will have 8 electrons. The third orbital will have 7 electrons, making a total of 17 electrons. Now we can write down the spins. The first orbital will get 2 electrons, which will be giving it 1 spin up, 1 spin down. The second will have a 2s with 1 spin up, 1 spin down. Now remember, when we go to 2p, we will remember Hund's rule. For each electron of the same energy, you put 1 electron in each orbital before doubling it up. So 2p will have 1, 2, 3 spins going up, and then we fill 1, 2, 3 spins going down. 3s will have 1 spin up, 1 spin down. 3p will have 1 spin up, 2, 3 spins up, and only 2 spins going down, so we can make a total of 17 electrons.
Another way we can figure out electron configuration is to use this method. It is an order of increasing energy levels. So all we would do would be placing an arrow down. So we would start with 1s, 2s, 2p, 3s, 3p, 4s, and so on and so forth. And then for our class, we only really go to F, so this would be our last orbital. So to expand a little bit more on this that we can use for the electron configuration, 1s pertains to this first period. S will always have only 2 electrons. The same here. P orbital will have 6 electrons. D has 10. So going back to the periodic table for hydrogen, it is in the first period, so it'd be 1s, and then it has 1 electron, so it'd be 1s1. For helium, it's still in the first period, but it has 2 electrons, so 1s2. Because s can only have 2 electrons, we now move to 2s. So 2s, 1 for lithium. This again, S again has 2 electrons. 2s1, and beryllium is 2s2. Now for this section right here, we're moving on to the P block. So we'll be here on P. So again, if we're doing this to figure out electron configuration, our arrow is going through 2p first. So 2p, it'll be boron 2p1, carbon 2p2, nitrogen 2p3, oxygen 2p4, fluorine 2p5, and neon 2p6. So we're done with 2p because p can only fit 6 electrons. Moving on to the third period, our arrow has now finished with 2p. It's going through 3s. So sodium will be 3s1 and magnesium will be 3s2. Because S can only fit 2 electrons, we're now done with this one. So moving on to the last period, the last section we will be doing. This block is again P. Our arrow has now gone through 3p. So same thing, 6 electrons only. 3s1, 3s2, 3s3, 3s4, 3s5, 3p5, 3p6. These are all p's. And that will be the last period we do.
So now we're going to go over a few important chemists that changed chemistry, and particularly they changed the topic that we have finished speaking about today. So the first one that we're going to go over is Max Planck, and he is known as the father of quantum theory, which states that radiant energy is emitted by atoms in small amounts rather than over a continuous range. Of course, we also have Albert Einstein, and he solved the photoelectric effect, which we talked about earlier in our video. And third, we have Niels Bohr, who developed a model of the hydrogen atom, which then led to the principal quantum number. And basically, after Niels Bohr discovery is when all of the other chemists started making their discoveries based off of his first discovery. Next, we have Louis de Broglie. I don't know how you say that, Louis de Broglie. He extended the description of light to all matter. So he actually extended Albert Einstein's original description of light. These are just a few of the important chemists that have impacted chemistry, and they're actually the ones that made up everything that we just learned in these videos. So now we're going to go ahead and do a review. Alrighty, so now that we have gone over all of the concepts that we're going to be covering in this video, we're going to go ahead and do some review over what we have learned. So we're going to start with the important formulas. So we got to calculate the speed of the wave, we must use U equals delta Y times V. We know that the speed of electromagnetic waves is and will always be 3.00 times 10 to the 8th unless we are told otherwise in our problem. We also learned Planck's constant, which is going to be 6.63 times 10 raised to the negative 34. This number is kind of like Avogadro's number. We need to memorize this and have it handy so we can plug it into our formulas. And the formula we use with this would be capital E equals H multiplied by C divided by delta Y. This can also be used to calculate the speed of the wave when we're talking about electromagnetic waves. The principal quantum number is the main energy level, and we also know that electron configuration is where we break the periodic table into the 4 different blocks, which are S, P, D, and F. We know that electron affinity increases from the bottom to the top as well as from left to right, which is the same for ionization. It also increases from bottom to top and left to right. And atomic radius is the trend that differs from the other two because it increases from right to left and from top to bottom. We know that these trends are very important and we must memorize them. We know that the wavelength is, of course, the horizontal distance between 2 points. Oh, excuse me. And we also learned that Hund's rule is for electrons of the same energy, we must put 1 electron in each orbital before we can double up. So that was just a quick review on everything that we've learned. Now, if you have any further questions, please feel free to email our professor at mdelga36@epcc.edu. And thank you all for watching. We hope you enjoyed our video. Please remember to like and subscribe and leave us any comments of any questions that you may have. Once again, I'm Brianna Delgado.
I'm Cynthia Garcia.
And I'm Cristina Guerrero.
And this was our video over Chapter 7. Thank you.